Okay, let's go for the next topic. The next topic is gonna be lenses. In general, we have two types of lenses, right? Converging lenses and diverging lenses. Now let's work with these lenses. Imagine that we have a converging lens, correct? This is the reference line, which is called the principal axis. And imagine that the object we're studying is far away from this lens, right? This lens right here. So imagine that the object is far away. When the object is far away, the rays are parallel to the principal axis, correct? Now we have a lens, it's a glass, right? When we have light going from air to glass, light is refracted. So we have a refraction right here, and it's found that these rays are refracted right to the same point. That point is called the focal point. So this is called the focal point. Right, symbol is F. Also, every time we have rays meeting in one point, that's the point for the image. So we have then an image right here. Image. From the previous chapter, we mentioned that we have two types of images, right? Real image and virtual image. If light is forming that image, right, the image is real. If no light is forming the image is virtual. In this case, we have light is coming, right, passes through the lens and passes through the image and forms the image. So means that this image is real. Real. Okay, perfect. Now let's do the same thing for the diverging lens. Okay, the same thing. We have the diverging lens right here. We have the principal axis. Again, we have rays coming from far away object, right? So the rays are then parallel to the principal axis. And what happens? Well, the rays are refracted because of this lens. But look, in this case, the refraction goes in this way. We have diverging rays in that way, correct? Well, but in this way, in this direction, we cannot find a point where the rays meet, but we can find it in this side, right? So this rays looks like they're coming right from this position, right? All of them looks like they meet in one point. It happens right here for the converging lenses, correct? So one more time, this is the point for the focal point, right? Focal point, and again, this is the points where we expect to find also the image. But one more time, rays are not forming this image because the rays are coming, right, are being refracted in this way and diverge in this direction. So light again is not passing, real light is not passing from this image. So in this case, we have that this image is virtual image, right? So we have then these two lenses taking or forming, right, different type of images. This is real image and this is virtual image. But in general, this lens can create actually also a virtual image. Let's do it. Imagine that we have a converging lens, correct? We have a converging lens like this, correct? And for this case, we have a focal point. You already found focal points, right? Because it's a double convex, right? So we have two focal points, correct? Now let's see what happens when we have an image. The object right here, the object, right? Object, right? Oh my God. Okay, and do one more time. Object, right there. Remember, we found the image exactly at the focal point when the object is far away. This is the case when the object is not far, it's close to the lens. Okay, to the lens. Let's see what happens then. Okay, let's do it. So in this case, we have that, remember the condition how we found the image? Well, we have the lens right here, right? And we use lines parallel to the principal axis. And what happens? Well, the ray is refracted and passes to the focal point. So we use this rule to find the image right here, right? Let's do it. So we have a ray parallel to the principal axis. How it's refracted? Toward the focal point. Perfect. Goes toward the focal, minus the focal point right there. Toward the focal point, right? And now we can go backward, right? Toward the focal point is refracted parallel. Okay. Toward the focal point is refracted parallel. Imagine. Okay, perfect. We have another one, a third ray, right? Pyramids are called rays, okay? Ray, right? Which rays for this description? Okay, we have the third one toward the center. Toward the center is now refracted. Okay, great. Now, in this case, the image is formed at this position, and the image again is real because real light is coming and passes through that point. Now let's move the object one more time. This is the lens. This is the focal point F. Now let's place the image, the object right there. Okay, object, perfect. Now, and one more time, let's try to find the position of the image. Okay, let's do it. So we have then the parallel ray, right? The technique parallel toward the focal point, parallel toward the focal point. Now toward the center, right? It goes like that. Imagine. Now it happens. It's might be too scary, but look, it looks pretty close, right? Okay, it happens that in this direction the rays are parallel. Means that they never meet. If they never meet, means we don't have image. But when we use the formula later, when I show you the formula tells us that actually the image is at infinity. Okay, special case, perfect. Now let's see what happens when we have the same lens right here and focal point right here, and we place the object now in between the focal point and the lens. Okay, let's do it. So the same thing, this is the technique, right? Toward the parallel to the principal axis, it goes toward the focal point, correct? Now toward the center, it's not refracted. See, as you can see, in this case, in this direction, right, the rays diverge, but when we're going backward, they look that they meet in one point, right here, in that point. And that's the point for the image. Okay, perfect. So we have an image right here, but this image is not formed by real light, right? This image is formed then because of the connection of this direction, right, going backward, and the points where they meet, we have the position for the image. So in this case, we are dealing with a virtual, right, image. Got it? So using a converging lens, we can create real images. We can create virtual images at infinity, and we also can create virtual images. Okay, perfect. Now let's try to find a formula that helps us to work with the object, right? Distances, the distance to the image, right, and so on. Okay, let's do it. Let's do it. Look, when we have a lens and an object, right, we have these three quantities that are very important to describe, right, the function of lenses and light, right? Okay, imagine again, this is a converging lens, correct? This is focal points right here. Imagine that we have the object right here, correct? Now let's create or find the image. Okay, let's do it. It's gonna be a right parallel, goes toward the focal point, right? Toward the focal point, correct? It goes parallel, correct? Toward the center, right? It's not refracted. Imagine. So what is the image? Well, the image is located right there. Now let's label these quantities. Look, right here we have the focal point. So the distance from the focal point to the lens is called the focal length, right? Focal, right, length, perfect. And the distance from the object to the lens is, let's label it as DO, distance object lens. And the distance from the lens to the image, right, to the image is labeled the I. Distance lens to image. Okay, perfect. Now, well, let's see what happens, how we can find the focal length. Well, the focal length is found in this way. Imagine that we have a lens, right? You have a lens, you have a screen right here, right? And you have as a reference a building which is far away, right? So you're trying to find the image of the building right on this screen. So you play with the lens going back and forth, right? Once you get the best image on the screen, the distance from the lens to the screen is the focal length. So this is one way how we can find the focal length of a lens. Okay, perfect. Now let's try to find the equation. Great. To do that, let's look for triangles. Okay, triangles using this figure right here. Okay, look, we have right here these two triangles. Look, we have this triangle right here, this triangle, and we have this triangle, right? These are similar triangles. How similar triangles are related or we work with? Okay, imagine that we have this triangle, we divide it by 2, and we label this as A, right? And then the largest distance as big A, this is B, and this is big B. Okay, perfect. And this is the angle theta. So if we use tangent, right? Tangent theta is equals to what? B over A is equals to what? B over A and B, right? Over A. Perfect. What happens right here? Okay, B over A. So let's do the same thing for these two triangles, right? These are similar triangles, have the same angle, right? And so on, similar to this one. Okay, now what is this height? Okay, this height, let's call it HO, the height of the object, and this one is HI, right? The height of the image. Okay, perfect. Now let's create similar triangles, right? So what do we have? Again, these two angles are the same, this one and this one are the same. So we can say that the tangent is opposite over adjacent, right? Opposite is HO over adjacent, which is what? The focal length F, correct? Must be equals to opposite right here is HI. By convention, because the image is upside down, we just label that as negative. Okay, perfect. Divided by what? Divided by the adjacent, which is what? Is this distance minus this distance, correct? It's gonna be VI minus, right, the focal length. Perfect. Now let's arrange this in this way. Look, we can say that HI over HO, right, is negative, is equals to, just use cross multiply, correct, is equals to, okay, what do we have? It's equals to VI minus F over F, correct? Okay, perfect. Now let's go to another triangle, right? Let's find another triangle from this figure, similar triangles. Look, we have in this picture another similar triangle. Look, let me use this. Let me see if you can do. You can see, right? This is the object. This is the lens, and look, the image is right here. Let me use that line that goes toward the center. Correct. Look, this one toward the center, and we create these two triangles, right? This one and this one. Look, these two triangles. You see it? Again, this is HO and this is HI. You see the triangles? Okay, it's gonna be this one and this one, correct? Perfect. Then again, these two angles are the same, correct? Because this is parallel to this one and this line is the same line. Okay, perfect. So these two angles, right? Let me see. I'm taking the right one. No, look. It's gonna be this triangle and this triangle. Why is I'm taking that one? No. Okay, so it's gonna be then this triangle, right, and this one. These two triangles right here. Got it? Perfect. So these two angles, right, are the same. Correct. Okay, great. The other one was the same. It was the same too, right? What's the other one? Because it's half. But let's use this one. Okay, so this is what this height is right here. It was the same actually, but before HI. Okay, the same height. Perfect. Now let's do it. Let's use similar triangles. And what do we have? The same angle right here, so it's gonna be HO over this distance. What is distance? DO. Okay, DO is equals to HI. HI, remember, it's negative because it's upside down. The image right there. Okay, perfect. Divided by this distance. What is that distance? Is this distance right here? DI, right? Gonna be DI. Perfect. Let's try to create a relationship similar to this one. And what do we have? We have one more time. HI over HO negative must be equals to let me see right here. Let's just cross multiply. It's gonna be VI over over what? DO, okay, DO, correct? Now this two, this quantity is the same as this one, so this one must be equals to that one, correct? Okay, let's do it. Perfect. Now let's try to relate those two quantities, correct? Perfect. And then we have that, where we are, right here, okay. We have di over do, which is this one right here, must be equals to, by the way, also this one, this quantity is called magnification, okay? It's also called magnification, okay, perfect. Great, so this is equals to what? This one is equals to di minus f over f. Okay, great. Now let's continue, okay? It's equals to di over f minus 1. Right here it stays the same, right? Di over do. Perfect. Now let's divide by di. When we do that, we have 1 over do, correct? Equals to 1 over f minus 1 over di. Perfect. Now let's arrange it in the traditional way for this equation. It says 1 over do plus 1 over di is equals to 1 over f. Right? 1 over f. Perfect. 1 over f. And this is called the thin lenses equation. Thin lens right equation. Correct? So this equation is the same as for the spherical mirrors that we covered the previous video, right? Part 1, this is part 2, correct? So it's the same formula, you can see. It's the same formula. Great. Now, also we have some properties for these quantities. We have that the O, for example, is positive for object, right? Object to the left of the lens, right? And DO is negative for object to the right of the lens. What about DI? DI is positive for real images, right? And DI is negative for virtual, right, images, right? What about F? F is positive for converging lenses, right? Lenses, and F is negative for right diverging lenses. Okay, for diverging right lenses. Correct. Okay, let's use these statements to solve problems. Let's do only one for this situation. Isn't a combination, right, of two lenses. That's more exciting. Okay, let's do it. Okay, let's do it. Imagine that we have this combo, two lenses, right? You can do this in the lab if you want to, and double check it. You can double check in the lab, right? We have two lenses right here. This is lens 1, f1, right? Then we have lens 2, right? f2. We have the object right here, object, and this is the data. Okay, this is the data that we use. Okay, sorry, that we use for this case. Look, let's take DO. DO, remember this is DO from here to here is DO1 for the distance for the lens 1. DO1 is equals to 28 centimeters, correct? And we have F1 equals to 15 centimeters, correct? F2 is equals to 19 centimeters. And the distance between these two, let's call it just D, right? D is equals to 14 centimeters. What else do we need for this problem? That's it. Also, we're looking for DI2, right? The image formed by the last lens. Okay, that's gonna be DI2. Okay, let's do it. First, let's try to find the image formed by F1. Okay, let's do it. So we have the beginning only one lens, right, like this. So we have the object right here. Now let's find di1. Okay, di1, right, is equal to square root of what? Okay, from here, let's solve for di, right? Why square root? I don't know why square root. Do a square root right here, and a square, right? Equals to what? Parenthesis right here. Equals to 1 over f, right? 1 over f minus, right? 1 over, this is like 1 because it's length 1, right? 1 over d of 1 inverse. Okay, so when we substitute the values, it's gonna be di1 equals to 1 over, what is f1? F1 is 15, right? 15 minus 1 over d01. d1 is 28, right? 28 inverse. Okay, let's do it. Let's take the calculator and let's do it. Okay, it's gonna be 1 over 15, correct? Minus 1 over 28, correct? Now this one inverse. Where is the inverse? Right here, I found it. Inverse. Okay, great. Equals to 32.3. Okay, 32.3 is equals to 32.3 centimeters. Right? Okay, perfect. Now the distance, look, from the second lens is gonna be 14. Okay, let me label right here. This quantity di1 is equals to 32.3 centimeters. Okay, look, means that the object is right here, and the image is gonna be, let's say, like right here. That's the image, right? Because this is this distance is 28. This is 32. It's gonna be. We'll make it to scale. Imagine. Okay, kind of. Okay, like right here. Okay, perfect. Now let's bring the second lens. Okay, let's do it. So let's bring it right here and let's place it right here. Okay. Now this image is the object for the second lens, right? Let's bring it down, right? It's gonna be right here. Imagine. Okay. Right there. Okay. Now what should be this distance? This distance is dO2, right? dO2, but dO2 is gonna be negative because of the convention. Remember, if the object is to the right of the lens, and the distance, right, is negative. Okay, let's find that distance. We found that from here to here is 32, but from here to here is 14. Oh, well, it's 14, right? So 32 minus 14 is gonna be this distance, the difference. Okay, let's do it. 32, actually 32.3 minus 14. So it equals to 18.3. 18.3, right, negative centimeters, correct? So this is gonna be now the object for lens 2, F2 right here, this is F1. Okay, perfect. Now one more time, let's find, remember looking for di2, let's find di2. Let's do it. Let's go for the equation. di2 is equals to what? 1 over F2 minus 1 over dO2, right, inverse. Perfect. So it's equals to 1 over, what should be F2 in this case, 19, right, minus 1 over negative 18.3, correct, inverse. And what is that? Okay, one more time. Let's use the calculator. And what do we have? 1 over 19, correct? This becomes plus 1 over 18.3, correct? I got it. Perfect. Inverse, okay, negative 1 equals to 9.3. Okay, so the answer is 9.3. 9.3 centimeters. Correct? Now, in the experiment, because from the experiment, in the experiment is found that di2 from the experiment is equals to 10 centimeters. Correct? And look, from the theory is found that's equals to 9.3. Well, it's very close. It's very close. The answer is very close. See, again, this is one example of how we can work with a combo. And in the case when DO is negative, usually when we have only one lens, right, or two lenses, right, we work with DO positive, the distance from the lens to the object. But sometimes, like in this case, we have a condition where that distance is negative. Right, okay, and with this we finish this chapter and see you in the next chapter.